Chapter 8, Exercise Set B. This exercise set is rather peculiar in that you have to use multiple methods for a single problem. Here is problem 1, and look at this context part. Compare that with that of problem 2. They are exactly the same. In short, problem 1 and 2 are identical, except, of course, the subpart here, 2.1 through 2.5 here. You can use these sub-problems as a guidance to solve a single problem. Or you can use 1.1 through 1.5 as a step-by-step process to solve this single problem. If you follow 1.1 through 1.5, that method is called the critical value method. If you follow 2.1 to 2.5, that method is called the probability value method. The preferred method by our textbook is probability value method, this one in problem 2. But over the years, I found that most of the students who are making high scores in classes were using this method, and the students who had been using probability method generally, not always, but generally scored lower scores. And also there is a bit of a reason behind it. This one is more intimately connected to the theory behind the hypothesis testing. Consequently, it's a little bit harder to understand. Nonetheless, this is the most preferred method by our textbook, so let's talk about it. For the other method, please refer to a separate video. Okay, here we go. Do you drink the recommended amount of water each day? Most Americans don't. Americans drink 4.68 ounce servings of water each day. A sample of 42 education professionals was randomly selected, and their water consumption for a 24-hour period was monitored. The mean amount consumption was 39.3 ounces. Assuming the amount of water consumed daily by adults is normally distributed and the standard deviation is 11.2 ounces, is there sufficient evidence to show that education professionals consume, on average, more water daily than the national average? Use alpha value as 0.05. This problem came from our textbook, 8.163. And here's a source from the problem as a matter of fact. Okay, let's go. First problem, explain why the normal distribution, or alternatively called z distribution, is appropriate in this case. This part is intended partly as a hint, partly as a theory. Even if you cannot answer 2.1, this problem gave you a hint. Use the z distribution, so you can go ahead and use this table and this curve and answer the other problems. Well, okay, let's go ahead with 2.1. There were two cases that you could use the normal approximation. One, large sample size, roughly speaking. Two, when the population standard deviation was known, again, roughly speaking. In this case, sample size is 42, too small. It's got to be the other way around. How do you know this is population standard deviation? Well, it came with the same sentence as the part that describes the population, assuming the amount of water consumed daily by adults is normally distributed. Yes, it's talking about American adults, not just 42 education professionals selected. So it came from the same sentence as the one describing population. So this standard deviation, even though it was not specifically described as population standard deviation, it is sigma, not S. Now, what if this 11.2 came with the same sentence as the sentence that describes sample? In that case, you have to use S, the sample standard deviation, not population standard deviation. But in this case, it's population standard deviation. And here goes the short answer to it. The population standard deviation is known. Now, I'll accept the short answer as a full credit, but it's not really perfect. So for the student who want to go a little bit deeper, here are further explanations. There are, roughly speaking, two situations that the normal approximation applies. One is right here. The inference is about the mean. Is it about the mean? It talks about the mean on average, yes. Okay, this works out. And then it considered simple random sample. Oh yes, we're talking about the randomness. So yes, we are doing the same thing over and over again, independently. And finally, large sample size. Oh, not really. Sample size of 42 is too small. So the central limit theorem doesn't apply. So the first criterion fails. How about the other criterion? Well, it's about the mean, yes. Next, the population is believed to be normally distributed. Is that true? Yes, indeed. Here it is. Explicitly, this part was describing the problem. Normally distributed. Okay, and we already talked about the standard deviation part. The textbook authors did not specify this was population standard deviation, but you should see that because it came from the same sentence as the one that describes the population. So the second criterion applies, and you can say that yes, the normal approximation works. Okay, that was really a perfect answer, worthy of 3000 level math course, but in 1000 level, the short answer is acceptable with full credit. Next, let's build hypotheses. What does a null hypothesis look like? The population mean, which is typically represented as Greek letter mu, equals to a certain number. We don't know that number, so let's tentatively name it as mu0. And then we have to describe HA later. Now, what is a candidate for this mu0? We have a number of water consumption here. 4.68 ounce servings, which corresponds to 36.8 ounce, and that's one. And 39.3 ounce, that's number two. And 11.2, there's another. I don't think there's anybody who would get confused with 42 here. It's clearly the sample size. Which is it? 36.8 or 39.3 or 11.2? Let's go with wrong answer first. Standard deviation is 11.2. Explicitly, the problem says this is standard deviation, so that's out. So we are down to two, 36.8 or 39.3. This one came from the sample. And what does the null hypothesis mean? In dictionary meaning, null means nothing, right? So you have to get null hypothesis or null number even if you did nothing. This came from sample. You have to actually do something. You have to actually do some sampling to get this figure. This is not going to be the null hypothesis. Anything that comes from the sample is not null value. So this is not it. This is the right one. As a matter of fact, our original problem in our textbook didn't have this part. It simply said 4.68 on servings, and you have to actually find out 36.8 as kind of computation. So this adjustment made the problem a little bit easier. Anyway, here we go. So that's null. So that's going to be alternative hypothesis, right? The other number. Is everything looking good? No, something is wrong. The alternative hypothesis is wrong. This number should be the same as the null. If you have two different numbers, then your chance is alternative hypothesis is wrong. You have to have the same number, mu naught, as before. What's the difference? Difference takes place here. The real mean has to be either significantly less or significantly more, or meaningfully different. Which is it? Well, the third case is rather rare. And if you look at the problem, if you read the problem more carefully, the problem explicitly says more water. So which is it? Bigger, less, or not equal? It should be significantly bigger. That's one indicator, more water. There's another indicator right here, 39.3. The sample statistic, which came from observed mean, is 39.3. That's clearly bigger than 36.8. So if you didn't know anything about it, then maybe the third one, not equal part, may make a little sense. But once you know the sample statistic and this sample mean, observed mean, then I think the third one, getting not equal right over here, doesn't make much sense. It's rare. It's going to be either bigger or less, and it's bigger because 39.3 is bigger. And of course, there's another reason, which is even more important. The problem explicitly said more water. By the way, this is the answer key. Okay, now that the hypotheses are set up, let's go over to the picture. How do you draw the picture? Here is the general process. Outline, center, end, and finally shade. The outline, draw the normal picture, going up and down, symmetric, unimodal, and so on and so forth. What's the center? Center should be the null, 36.8. End is a little bit tricky here. We have to use observed mean of 39.3. That is the essence, one of the essence of probability value method. In problem 1, critical value method, we use different value. We use critical value here and find out. Here in method 2, we simply use 39.3 and just shade. Blue part and then red part. Now, a little bit confusing part begins from this point on. What does this p-value, this red area, mean? What is the meaning of this red part? Well, here we go. And roughly speaking, this is probability of type 1 error, which means the probability, assuming that null is right, mu is indeed equal to 36.8. The sample mean ends up with 39.3 or higher, just by mistake, just by randomness. If that probability is sufficiently high, what does that mean? Oh, here comes another confusing part. You want to minimize a type 1 error, so that's not good. So if this p-value is too big, then you fail to reject the null hypothesis. And how big is too big and how small is small enough? That's the alpha value, 0.05. So the purpose here is to calculate this p-value and compare that with alpha. How do we do that? Calculating p is not too difficult. You can just do this. Z equals to end minus center over SE as before. And that's approximately equal to what? 39.3 is the end. 36.8 is the center. How about SE? It should be standard deviation over square root of n, where n is the sample size. This is therefore 11.2 over 42. And you can run your calculator to find out the z-score. Based upon this z-score, you can look up your z-table and get an estimation of this probability p. Once you find out that p, then you can go ahead with the comparison. Well, here is the computation. Oops, what did I do? Okay. This is the cell I wanted to open, okay. And let me copy and paste the same picture over here. n minus n2 over SC, calculating, we get 1.44 something, approximately 1.45. So looking at the z table, 1.45 is back here, 1.4, row is here, 1.45, okay, 0.9265. So that's the probability of left-hand side, the blue part. So the probability p-value is 1 minus 0.9245, and approximately you're going to get something. By the way, everything is approximation, so we need wiggly equality sign, not strict equality sign. And you calculate something. By the way, I use technology to do a little bit more accurate computation using more decimal digit, and I ended up with this computation, 0.074 something, a little bit better than the table method, but table method will do just fine. Let's use a little bit more accurate figure. The p-value here, the red area, is 0.07. What does that mean? This measures type 1 error. The probability of type 1 error is too big, bigger than alpha. So does it mean H0 or HA? A little bit confusing. Well, that's the nature, I'm afraid. That's the nature of the probability value method. And I think that is the reason why the student who used probability value method generally scored lower than the student who used critical value method. Anyway, here it is. P-value is, roughly speaking, probability for type 1 error. That is, you end up getting the x bar value or higher, even more far away, as your sample mean, given that real mean is about the same as mu 0, which is the essence of H0. And you calculate like that. P is too big, so reject HA and accept H0. Or another way of saying it is we fail to reject H0. So we fail to reject the null hypothesis. Or there is not enough. There's not enough evidence to overturn the null hypothesis. There are different ways to say, and these are kind of formal, but I will accept other kind of languages too, like informally reject HA and accept H0, and another one like H0 wins, those kind of things. But then again, this approach is a little bit trickier because after getting the p-value, how does that connect to the conclusion? That's a little bit tricky. And if you get a little bit too confused, then I advise you to go back to problem number 1 and study critical value method. That one is far more explicit and graphically clear. By the way, here is a rough description of this part, this type 1 error or p-value. This isn't really accurate, but it works like charm for most of the problem. Not all, for most of the problem. Roughly speaking, the p-value is the probability that null is right. And if that's big enough, then H0 is good enough. If that's too small, then H0 is no good, so throw it away. Okay, don't tell anybody this is accurate. I don't want to spread this one around, but use it as a kind of gimmick method to apply the probability value approach.